In this video, we're looking at continuous stats. This is all normals, PDFs, confidence intervals, sampling distributions, central limit theorem. Make sure you got your SACE formula sheet. Make sure you got your calculator, and we'll make a start. So we've got straight up a normal distribution question. So they haven't said what x is in the context of the real world, but you should still pop this line in, x squiggle n 620 13. Remember, this is a real life question. You've got to have that line, let x be whatever it is. So 600 less than x is less than 630. We can roughly work out what this probability is. Okay. Stats, we're going to go in there, and then distribution on F5, normal on F1, and NCD on F2. There's 600 to 630, 13 for the standard deviation, and 620 for the mean. We're going to execute that, and we'll get 0.717. Probability that we're greater than 652. Similar premise, we're just going to set the lower to 652 and the upper to a whole bunch of 9s. We'd like to put infinity ideally, but there's no infinity button on the calculator. 6.91 or 6.92 times 10 to the minus 3. Now, if this ever happens, that's scientific notation. So you can move the dot back 3 spots. So that's 00692. So the dots move back 3 spots. That's what the minus 3 does. Okay, next is an inverse normal question. So realistically, what we'd like is to find a k-value, and anything less than that k-value should have a probability of 0.3. So dist, norm, inverse norm, the tail is a left tail, and the area is 0.3. The mean and standard deviation are the same at 13 and 620. And then we're going to just execute that. K roughly equals 613. We'll go to 3 significant figures. Now I want you to double check this in the test if you ever do it. So normal NCD, if I go for the lower being minus a whole bunch of 9s and the upper being the K value we just found, I should get about 0.3 for my probability, which I do. Okay, next we got a z-score question. So his z-score, well in general, z is the score take the standard deviation, the score take the mean over the standard deviation. And I reckon might actually be on your formula sheet. Yes, it is. Right there. Okay. So find your z-score for each trial. So we've got 100 meters, we've got 400 meters, and we've got 1000 meters. So the Z100, I might call this one Z400, and why not? I'll call this one Z1000. Okay, so this is his time, 26.2 minus 27.1, all over the standard deviation, which was 3.1. I'm hoping it sort of makes sense that the standard deviation is smaller for the lower distance runs. Because it's shorter times that people are running overall, you would expect less variance in those times, just because there's like less time in total that they're running. Minus 0.290. I'll show the 0 because we're going 3 significant figures. Z400. So this one here is going to be 109.2 minus the mean 107.6. all over the standard deviation of 11.2. And we can work that out. So 109.2, 107.6, and 11.2 on the bottom, 0.143. And Z of 1000 is 281.4, 283.6, and 35.8. So we'll work that one out. Wonderful. Minus 0.061. Okay. So best to worst. So make sure you actually give a scale for which is good and which is bad out of first, second, and third. Because otherwise I might not know if you mean that 1 is good or 3 is good. So the best score is the lowest time. So this is 100 meters. And then this next one would be 1,000 meters. And then the next one would be 400 meters. So the Z here is minus 0.290. So that's the lowest Z score. Minus 0.061. And here it's actually positive, so he's above average for this run. Because we're running, lower Z scores are better. If it was something like marks on a test, you'd want higher Z scores because you'd want higher marks. Okay, so we've got a bit of information here. We want to find the mean. 22% of people can run a 2,000 meter sprint in less than 566 seconds. So I'm going to go 566 there. There's my bell curve. And that would be the X score. I would like to know the Z score. We know that 22% of people are there. Okay, so this Z score here, I can work out with an inverse normal. So we're going to go into stats, dist, norm, inverse normal. The left tail, the area is 0.22. The standard deviation is 1 and the mean is 0 for a Z score. So we're going to execute that, minus 0.772. Cool. You don't need to write how you got that, but it's this inverse normal here. So it's Z is X take mean over sigma, and we should have 3 out of 4 of those things. So sigma is 72. I think we knew what the Z score was, so we just got that, minus 0.772. And we got X take the mean. So what was it? X was 566. And we've still got the unknown mean. Now, I might actually use the full version, just so that we don't make any weird rounding errors. So 0.7721932. I know that it seems like not a big deal, but sometimes when you're working like this, if you like square a number, for example, it's going to blow up and little differences will become big differences. So it's important to use the full version of the number until you're actually done with the working. 72 times minus that number is 566, take the mean. So if you rearrange that, therefore the mean, bring that onto the left and bring all the other stuff onto the right. 566. This is going to be take 72 times minus the Z score. But you'll notice there's 2 takes there, so I'm just going to turn that into a plus. Okay, and we should be able to get that. So 566 plus 72 times 0.7721932. There we go, 621.597. So roughly equals 622 to 3 significant figures, and this is in seconds. Now this is one that you absolutely need to double check. So if you go into stats and then distribution normal NCD, and your upper was 566 and your lower was minus and then a whole bunch of 9s, your standard deviation was 72 and the mean was what we just got, 622 approximately. Then we should get 0.22 or 22%, which I do. The reason I don't get exactly that is because I have rounded the mean, but that's pretty much what it is. What is an assumption you've made? Through all of this, we have assumed that running times are normally distributed. You might notice nowhere in the question I said that it was normally distributed. We sort of just assume that by calculating Z scores and doing all this. It all relies on them being normal. That's probably a reasonable assumption for running times, especially if you're looking at athletic trials where people are specifically trained for it and there's less like jagged bits of the distribution. But the question has not said it. Okay, suppose f of x is a valid PDF, show that a is 1 over 9. So valid PDF tells us that 1 equals the integral from 0 to 3 of f of x. So 1 equals 0 to 3 of ax squared. So 1 is a, the integral from 0 to 3 of x squared. Now, there's sort of 2 ways you can go about this. Since it's a show that, I will be doing the integral by hand in this video, but just to make sure that you got it right, or if the question was just like find a, it would be, you could just work out what that integral is, so it's 9. But I will do it by hand. So 1 is a times x cubed over 3 from 0 to 3. So 1 is, we could write a over 3 there, but then you get x cubed from 0 to 3, just pulling out the 3 there. 1 is a over 3 times 27, take nothing. So 1 is 27a over 3. I'm going to run out of space here. 1 is 9a, therefore a is 1 over 9. Now, you absolutely can prove this by just setting a to 1 over 9 and then doing the integral. So if we integrate literally 1 over 9 x squared, that doesn't work. 1 over 9. If I do that, I get 1. But quite often these questions ask you to find a. So the process that I've just used, you can find a. And if the question just says find a directly, then you can just do the integral on your calculator. Okay, calculate the probability that we're between 1 and 2. So we need to write down the integral we're going to do, but we can do the integral on our calculator. So this would be the integral from 1 to 2 of our function, which is the integral from 1 to 2 of 1 over 9x squared, now that we know that a was 1 over 9. So this roughly equals, and we can do that integral on our calculator. So we're going to have 1 over 9 there, and have x squared there, and we're going to go from 1 to 2, 7 over 27. So this equals 7 over 27, but it's a probability, so they usually like it as a decimal, so it's about 0.259. And calculate the mean. So the mean, there is a formula for this, and I reckon it's even on your formula sheet. So there it is, x times f of x. They're integrating from minus infinity to infinity on the formula sheet, but what that really means is whatever bound your function's on. So in our case, integrate from 0 to 3. So 0 to 3 of x times the function. This is the integral from 0 to 3 of x times 1 over 9x squared. Don't waste your time doing it by hand. So we're just going to integrate that. So x times, and then the function itself. So 9x squared. You don't really need the brackets there, but I like to just in case. We're going to integrate from 0 to 3, 9 over 4. So I guess this specifically equals 9 over 4, which is 2.25. Next, we've got to calculate the standard deviation. So there it is. So x, take the mean squared times f of x. So sigma is the square root of, this is integral from 0 to 3 of x, take the mean squared times f of x. And if we plug in what all those things are, this is 0 to 3 of x minus the mean was 2.25. So we're going to square that, and we're going to times it by our function. And we're going to take the square root of the whole thing. So I'm actually just going to go up and edit this integral, save me typing it out again. So instead of the x, it's going to be x take 2.25 squared. So I get that as a number, and just don't forget to take the square root. So it's approximately equal to 2.581. Beautiful. Okay, calculate the median. Now this one you do have to do by hand. So for the median, we require that 1/2 equals the integral from 0 to m of our function. We'd like half the area to be before the median and half the area to be after the median. So the median is m, that number. So 1/2 is the integral from 0 to m of 1 over 9 x squared dx. And then we can just step out what this is. So I'm going to go 1/9 out the front, but this is x cubed over 3 from 0 to m. And we can also pull out the over 3. So a half is 1 over 27 lots of x cubed from 0 to m. Okay. So this would be that if I times both sides by 27, 27 over 2 is x cubed from 0 to m. And then we can just do that definite integral bit. So this is m cubed take 0 cubed, and that's 27 over 2. Therefore, m is the cube root of 27 over 2. And we can work out what that is. You do have a cube root button on your calculator, or if you prefer, you can just raise it to the power of 1 over 3. But regardless, you're going to get this number, 2.381. Okay, first little check that we want to do is make sure that this number is actually in our range, and yes, it is, 0 to 3, so that's good. Then the next check that we'd like to do is make sure that if I integrate from 0 up to that answer that I just got, I should get a half. So integrate from 0 up to 2.38111578, a half. So yes, that median's correct. Okay, we've got a shop here. They sell hot dogs. Find the probability that a single hot dog is less than 83.3 grams. Let x be the weight of a hot dog in grams. Then we need to go x squiggle n, and then we need to give the mean and standard deviation. So 85 and 2.1. Okay, so that's the notation you absolutely need for normal distributions. Then we want to calculate the probability that x is less than 83.3. Now, whether you use a less than sign or a less than or equal to sign doesn't really matter when you do the calculation. But since the question asks for less than 83.3, that's why I've used the strict sign to sort of match the wording of the question, even though it doesn't matter when you calculate the answer. Okay, normal CDF. So my upper or my lower should be minus and a whole bunch of 9s. My upper should be 83.3. My standard deviation 2.1 and my mean of 85. Let's calculate that, 0.209. The question's asking for a probability, so we're done. If it asked for a percentage, it would be 20.9%. State the mean and standard deviation of S6. So the mean of S6 is 6 times the mean of X. Make sure these formulas go on your formula sheet for S6 and also for like X bar as well. This is in sampling distributions, this topic, or the central limit theorem if you want. So this is 6 times 85, which is something we can work out. Okay, so that's 510. We need units on here, so grams. Good. And the standard deviation of S6 is root 6 times the standard deviation of the original one. So this is going to be root 6 times 2.1. And that is 5.14 grams. Okay. Is it reasonable to assume that S6 is normally distributed? Now, normally we don't have enough information. So remember the rules are, well, the rule of thumb is if the number is bigger than 30, then it usually is. 6 is not bigger than 30. Or if there's like an earlier n value, which is, the question actually says that the hot dog individual weights are normally distributed. So yes, as the weight of an individual hot dog is normally distributed, stated above, then S6 should be S_6 when you write it, will be normally distributed. And really importantly, you need to say by the central limit theorem. You absolutely need to say the words central limit theorem in your answer. otherwise you may lose marks. Okay, calculate that probability. So we know that S6 is distributed normally. It's got a mean of 510 and a standard deviation of 5.14. This is from, let's see, this is from B and C. So we know that the mean and standard deviation from B, and we know that it's distributed normally from C. Therefore, the probability that S6 is less than 500 roughly equals, and we can work that out. So stats, dist, norm, and CD. So going lower is minus and a whole bunch of nines. The upper is 500. And then the standard deviation was root 6 times 2.1. I'm just going to make sure that I bracket that right. Otherwise, that could lead to issues. And then the mean was 6 times 85, which was 510. I'm just putting in the full versions because you really should use your full versions of numbers until you get your final answer. Do not round until the end. Can make a difference. Okay, so everything's in there like it should be. 0.025 or 0.0259. Okay. Yeah. Cool. Consumer law states that no more than 1% of the packs can be below the advertised weight, and they're advertised as 500 grams. Do they satisfy the law? No. No. Based on C, 2.59% of the packs are below 500 grams. Cool. Yeah, that's it. So no more than 1%. Yeah, that's it. You might also notice that I'm missing something here. I'm missing the interpretation because this question asks for an interpretation there. So the probability that the total weight in a pack of 6 hot dogs is less than 500 grams is 0.0259. So the question there just asks for an interpretation. Make sure you have it. Do they satisfy the law? No, because it's 2.59%. That is more than 1%. Okie dokie. Next, golfers trying out a new club. They will need the standard deviation, but they actually don't have it. They've got a sample standard deviation. So we don't know the population standard deviation. This is the sigma symbol there. So they'll need the population. Explain why we won't know sigma. Because we only have a finite, limited number of trials. Not the whole population of his swings. You can only ever get the sample because you can only take a sample of his swings. In theory, he could always do more, or like in the past, he's done more and hasn't measured it. We can use the sample standard deviation S equals 18.8 to approximate the population. All right. So yeah, we don't know the population, but we do know the sample. So we're going to use that to approximate it. And I'll draw the little sigma symbol above there. Okay. Using the data above, calculate a 95% confidence interval. So we're into stats. I'm going to exit out. So that's inter, so that's over F4, Z. And what are we at? One sample, Z. Confidence level is 0.95. We don't know the standard deviation, but we were going to approximate it with 18.8. X bar. So let's see, 208.4, the question says. And N was how many swings you did. So the 12 swings. That should be everything we need. So there it is, 197 or 198. and it goes up to 219. There's that confidence interval. Can we conclude that the new club has increased hitting distance? So old hitting distance was, I think, 200. Yeah. No. As 200 lies within the confidence interval, and numbers below 200, it is possible that the mean is still at 200 or below. So yeah, something like that. That is done for your answer, but so we would need the entire confidence interval to be over 200 to support this claim at the 95% level. So yeah, if the lower bound was like 203, then your answer to this question would be yes. Okay, the golfer concludes that if the confidence interval had a width of 16, he would know. Now, I want to talk a little bit why the golfer may have concluded this. So let's suppose that the width was 16. Then we go up and down by 8. So I'd expect the confidence interval to be something like 200.4 and 216.4. That would have a width of 16. And you can sort of see there, then we would be able to conclude that the distance had increased because the confidence interval is over 200. Okay. So explain how he came to this conclusion. So he is hoping that the CI looks like this, 200.4 to 216.4. So this is 208.4 is X bar in the middle. Width is 16 and whole CI to be over 200. So that's what he would like to actually conclude. Now, so let's calculate the n value. I think there was a formula for n value, but I'm not entirely sure if it was on the formula sheet. I don't think it is. So you do have to look that one up. Okay, so I've just written down the formula there for n. I do want to talk about where that 1.96 comes from. So because we're dealing with a 95% confidence interval, it's all good. That's just a formula. We're looking at an inverse normal. So if you wanted sort of a 95% confidence interval, you would expect 2.5% to be on each side. So we could get the Z scores for that. So if the tail was, let's go a right tail, mix it up. And I want 0.025 and then a Z distribution, so 1 and 0. I should get 1.96, which I do. So that's where the 1.96 number comes from. I'm hoping if you had like a 90% confidence interval, you'd have 5% hanging off each side, because that makes 10 in total. So if you had a 90% confidence interval, you would use that number instead of 1.96. But yeah, that's where those numbers come from, 1.96 and minus 1.96. Okay, we can work this out. So this is, I think we have the standard deviation. Where is it? Standard deviation, 18.8. He wants the width to be 16. And then we can just chuck that whole thing into a calculator. So let's do that. There we go. Okay, 2 times 1.96 times 18.8 all over 16. And we're going to square that answer. There. 21.215. It's about 21.2. Now, really importantly, when you deal with this n value, 21 is too small because we actually want 21.2. So therefore, we need 22 swings. Really important that you always round up. If you do a confidence interval with 21, you will notice that it's wider than 16, which you don't want. So not that you can, but if you could do a confidence interval with exactly this number, you would get exactly 16. But since n has to be a whole number, so this one is less than 16. And these are the widths that we're talking about here. So that's why you need 22 swings. Okay. The golfer does the confidence interval with 22 swings, and they get this. So why can we still not conclude that the new club has increased hitting distance? Because 200 still lies within the confidence interval. It is possible that the mean is still 200 or below, as low as 109.44. Yeah, which would mean that the new club hasn't increased hitting distance. Okay. Since this is a 1-mark question, if you had like just that sentence, that should be enough. You don't need to write that whole thing. Okay, so what went wrong? We were hoping that the confidence interval would look like this, right? That had a width of 16, and we would have been able to conclude that it was like over. 200 still lies in the confidence interval, so what went wrong? The key here is working out the sample mean. So for this confidence interval, so the new x bar value is the average of the lower and the upper. So 199.44 plus 215.16 all over 2. Okay, so we can work out what that is. $207.3 meters, I reckon. So that is the new x bar value. So when he did, I think more swings, because I didn't want to give you the answer. When he did the new trial with more swings, the sample mean changed, right? Old sample mean was 208.4 meters, but new sample mean was 207.3 meters. This shifted the confidence interval left a bit. So even though the width was less than 16, due to the new center of the confidence interval, we still have 200 within. So that's what happened. And this is a really important thing about confidence intervals, right? You could, there we go. You could, if we had this confidence interval like here, we could say like, oh yeah, 208.4 is the center. So let's just pretend we did an experiment and got the width to be 1. Then I could have my confidence interval being like this, and I'd get a really good idea of what it is. Now, I'm hoping you can see maybe why that's a really bad idea, because, yeah, 208.4 was the sample mean, but he's only done 12 swings. If he does another one, it's probably going to change the sample mean. And you can't just, like, in theory, you could say, like, oh, let's pretend that I used 1,000 samples, and then your confidence interval is heap skinny. And that sort of defeats the whole purpose of doing a confidence interval. So yeah, sample mean will not stay the same if you do another confidence interval. And that's the key here. The whole confidence interval is shifted down. So I think for your, you do it on like a number line. So 208.4. And then this was like the X bar original. And then the confidence interval here, 198 to 219. So we went all the way down to 198 and all the way up to 219. This is how you draw a confidence interval on a number line, by the way. And for here, the width was, let's see, 219, take 198, and the width was 21. So I might just draw that there. So he was really hoping that if he could just pull that width a little bit tighter, because the magic number here is 200 that he wants to hit. He tried to pull the width in so that it would just be like a little bit narrower and he could hit 200, which in theory was a good proposition, but the sample mean moved down. So on the new sample mean, that was 207.3. So there it is. So that's X bar new. And then that was still a little bit below 200. The 200 still inside because the sample mean shifted down, even though the width was a lot narrower. All right, the Shrek fan club. So there it is, 28 members. Determine the sample mean and sample standard deviation. So we just got a big list of numbers here. And we're going to chuck those all into our calculator, just in list one, because we've got a big continuous list. So 84, 53. I won't make you watch me enter these all. All right, there we go. So I've just gone and typed those all into the list there. And you can see that I've got 28 entries in total on my list, and the question says there are 28 members, or you can count them all up. So that's how you know. We're going to go calc. You've got to go set. Now, if you've got a frequency table, like two lists, your calculator would look like this. We have a big long list of numbers, so you want to hit the F1 button to make it 1. If you're dealing with a frequency table, that should say list 2. Okay, then you hit 1 bar. 69.5 is the sample mean. And the sample standard deviation, I should give approximates for these actually, was SX, so 8.67. Wonderful. Okay. So we got these. We want the 99% confidence interval. So you just exit out here, interval, Z, one sample, 0.99 for 99%. Standard deviation. All right, so let's see. We don't really have the standard deviation, but we can sort of use this sample again to approximate it. It's a little bit dodgy that we're doing that, but it's sort of close enough. It's the best guess we've got. And then X bar would be this number, 69.5. Okay. Now I'm going to be a little bit pedantic here and actually go back and use the full versions. So that's what they were there. And I'll just go and pop those in. Usually it doesn't matter, but sometimes it can really throw off your answers by quite a bit. So it's important just to use the full versions if you can. So 8.6772673 and 69.5357142. Wonderful. Okay, next thing we want to do here is change n. So there were 28. I will also mention we've got it on variable on the calculator. You can change it to list and it will use the data in your list. I'm just doing variable because that's how we've learned it up till now. And it might be a bit confusing to have two different methods that are so similar. 65.3, so we're going to go 3 figures. 65.3 is less than the mean of Shrek watches is less than 73.8. Wonderful. Okay. Using this confidence interval above, a reporter says that, there we go, is this reporter's claim justified? Now, normally it would be. So normally we would say yes, as the entire confidence interval lies above 50. However, have a think about why the answer might be no in this question before I write it out. However, the claim is about the average member of society, and the sample for the confidence interval was using data from the Shrek fan club. This sample is incredibly biased. So we cannot make conclusions about an average member of society. You know, most people probably have only watched Shrek 30 or 40 times, not 50. All right, cool. There we go. So yeah, normally you'd say yes, but the sample's biased. Okay, Arrival Club, the B movie, claims to be more dedicated. So there we go. The B movie, it is known that the mean of the B movie is 77. So that is just a known fact. They're 99% sure that the mean of the B movie is greater than the mean of the Shrek fan club. So yes, 77 lies in the entire confidence interval. You really should say the word confidence interval, but if you're short on time, you can just write CI. For Shrek lies below 77. So we can so at the 99% confidence level, it is supported that the mean for B movie is higher than the mean for Shrek. And when I say these means, I mean like number of times watched in each fan club. Okay, so that's how we answer that one. You don't have to worry about bias or anything because they're directly making claims about members of the fan clubs. So the samples are representative here. Now, if we want to get kind of technical here, we do have some issues. We used the sample standard deviation to estimate the population for Shrek, and we assumed the data was normally distributed. So yeah, these are absolutely issues, and you know, you'll get the full marks even if you didn't mention these necessarily, but it's sort of more evidence towards the A+ if you can identify some issues with your conclusion as well. Don't spend heaps long on the interpretation questions, but maybe come back and add some of this stuff if you get extra time. Okay, we've got a central limit theorem question. One of these is W and one of these is W15. A is W15 and B was W. So A looks more normally distributed. Not that the question is asking, but that's why. If these had scales on it, you would find that that's actually a bit narrower as well than W. Let W25 calculate the mean and standard deviation. So the mean of W bar 25, mean of W bar 25 is the same as the mean of W. These are your formulas from sampling distribution. So that's 18.2. And the standard deviation of W bar 25 is the standard deviation of W over root 25. So this is 0.3 over, and then root 25 is 5. So let's work that out. 0.06. Cool. Assuming W25 is normally distributed. Now, if the question asked you, actually, I think it does. So let's do that later. Determine the probability that that's less than 18. So W bar 25 is distributed normally. It's got a mean of, whatever we worked out that was, 18.2. It's got a standard deviation of 0.06. The probability that W bar 25 is less than 18 roughly equals and we can work that out. So let's do that. Stats, dist, norm, NCD. We're going to go minus 9999999, 18. And then we're going to give our mean and standard deviation 0.06 and 18.2. Execute 4.29 times 10 to the minus 4. This roughly equals 0.000429. You don't necessarily need to get it in, like, you could have left it in scientific notation, but I always like writing it in both just so we can interpret it properly. Okay, each box contains 25. The label says total weight is at least 450 grams. So the probability, all right, so if we want the total weight to equal 450 grams, therefore the average weight should equal 450 over 25. There's 25 boxes, or 25 packets in a box. Okay, so let's see if we can get this. So 450 over 25, it's 18. And what do you know? That's heavily related to our answer from before. Therefore, the probability that total weight is at least 450. This is the same as the probability that W bar 25 is greater than 18, which is 1 take the probability that it's less than 18, which is 1 take 0.000429, which approximately equals 1. Okay, now that's sort of, I'm assuming, the method that would be intended here. But this is using the answer from C. Now, if you're asked this question directly, this is a question about S25, not W bar 25, because it's the total weight of 25. So you could go for a normal distribution. We're asking for at least 450. So we're up to 450 and a whole bunch of 9s. The standard deviation for this would be, let's see what the original one is, 0.3 times the square root of 25. I think it's 25 boxes, isn't it? Yep, 25 bags. And the mean would be 18.2, the original mean, times 25. Now, if we do all of that, you basically get 1. So that would be the other way, using the S25 method. Now, why is it normal? So as W15, I can't type this, I got to use notation. As W bar 15 already appears normal. Apologies about my handwriting, normally distributed. From histogram A. W bar 25 will be more normally distributed. By the, and you have to say this, central limit theorem. If you're running out of time, you can say CLT for like a acronym, but it's better if you write out the whole thing if you do have time for it. And that's it.